Today in Chapter 12, Chemical Bonding, we're going to take a look at molecular structure, and we're also going to look at the VSEPR model with both single and double bonds and finish up the chapter. So let's start with molecular structure. So by definition, a molecular structure is a three-dimensional arrangement of the atoms in a molecule. So this denotes here in this first molecular structure a linear molecule, and it has three different atoms. This one is a triagonal planar, and we're going to get these shapes down here in just a little bit, go over those. And this is the 3D model of a tetrahedral molecule. So by definition, you just need to know what a molecular structure is. So a linear structure are atoms that are in a line. So carbon dioxide, for example, is an example of a linear structure. So this would be what it would look like if we wrote it out. This is what the molecular 3D structure arrangement would look like. Boron trifluoride, remember boron's the one that's the exception where it has only 6 in its outer shell instead of 8. It forms a flat planar molecule, and we call it a trigonal planar molecule, and that's the bond angles that are located between. That's as far away as those fluorines can get from each other, and they are 120-degree bond angles. And that's called trigonal planar. It's all in the same plane. This is a tetrahedral molecule. This molecular structure here is hard to see because it's flat and not 3D actually to be able to see, but this is a ball and stick model of methane, and this is a tetrahedral structure. And I'll go over this more in class with an actual ball and stick model and give you a set to take home to practice the different structures with. The VSEPR, VSEPR model, is the valence shell electron pair repulsion model of the atom. The structure around a given atom is determined principally by minimizing the electron pair repulsion. They try to get as far away from each other as possible. So, if there are two pairs of electrons that are free in this case, it's 180 degree and it's called linear. So here's the example. That's as far away as those two chlorine molecules can be from each other, and it forms a 180-degree bond angle. Three pairs of electrons form a trigonal planar with 120-degree bond angles, and it's all in the same plane. Four pairs of electrons have 109.5-degree bond angles, like we saw in methane a while ago, and that's as far away as they can get from each other. And like I said, the ball and stick model will help in class as well. So how do you predict the molecular structure using the VSEPR model? First of all, you have to draw the Lewis structure. You can't get out of drawing Lewis structure in order to start your VSEPR model. You count the electron pairs and arrange them in the way that minimizes repulsion, so you're going to put the pairs as far apart as possible. Then determine the position of the atoms from the way electron pairs are shared. So how electrons are shared between the central atom and the surrounding atoms is how we'll lay that out. And then determine the name of the molecular structure from the position of the various atoms around the central atom. So you have a chart like this in your textbook, and this is number of electron pairs, number of bonds, what the electron pair arrangement would look like. Here's what your ball and stick model would be like, what we would call the molecular structure, and this is a partial Lewis structure, just a generic one, and then the ball and stick model. So this would help us to determine if we're dealing with a linear, a trigonal planar, or a tetrahedral. Now notice on the tetrahedral, if we have 4 bonds, we have 109.5 degree bond angles, and our molecular structure, if we have a central atom and 4 elements past that, 4 atoms past that, going around it or surrounding it, each one will be filled. The ball and stick model is going to look like this, and that's called a tetrahedral. So the electron pair arrangement is tetrahedral, and the molecular structure is tetrahedral. If we only have 3 bonds, it's tetrahedral still because we still have that same setup. The only thing is we have an atom at 3 positions and a pair of unshared electrons at the 4th position. So if you look at the ball and stick model, we have 3 and then 1 unpaired, so there's nothing up here. So even though it's a tetrahedral electron pair arrangement, because there are 4 sets of electrons that are equally spread out, what we actually would see is called a trigonal pyramid. If we only have 2 bonds, we still have the electron pair arrangement as tetrahedral, but notice on this, we see a bent or V shape. This isn't linear, and again, the ball and stick model in class will help. but it's called a bent or V-shaped, because what you actually would have is an atom here, and then the central atom would have two sets of unshared electrons, unpaired electrons on either end of it, making it the bent or V-shaped. When we look at double bonds using the VSEPR model to predict the molecular geometry of a molecule, or a triple bond or a double bond is counted the same as a single pair of electrons. So for example, this is carbon dioxide. It's a double bond. Those double bonds are going to form a linear formation. So this says to determine the molecular structure for each of the following molecules and include the bond angles. So what you have to do is start off with your Lewis structure. So we have 1 electron here, 4 here, and we have 5 here. So my total that I have to use are a total of 10 electrons is what I have to come up with. Carbon's going to be my central atom. The duet rule is all that's necessary for hydrogen. We'll bond it to nitrogen. And we have 2, let's do 4, 6, 8, 2, 4, 6, 8. And hydrogen can only have those 2. So 2, 4, 6, 8, 10, 12, 14. I have way too many electrons. So what I'm going to have to do, I can only have 10. Let's double bond, which is going to cause us to take a pair of electrons from here and from here. 2, 4, 6, 8, 10, 12. We still have too many electrons. So what we're going to do is we're going to bond again, triple bond here, and let's take off these and these. So 2, 4, 6, 8, 10 electrons, which is what we wanted. Make sure the octet rule is followed, 2, 4, 6, 8, 2, 4, 6, 8, and then the 2 for the hydrogen. So this is our Lewis dot structure for this. Notice that we only have 1 unshared pair of electrons out here on the nitrogen, and it's an outside element, so we really don't have to worry about that. Our central atom has all of its bonds taken care of. But what's going to happen? What's it going to look like when we put those in a ball and stick model? You can imagine this is going to end up being a linear or a straight line. So the answer for this one, for the HCN, is linear, and that would be 180 degrees. Let's take a look at pH 3. Phosphorus has 5 electrons in its outer shell. There are 3 hydrogen with 1 each, so that's a total of 3. So we have 8 electrons to deal with. We're going to put phosphorus as the central atom, hydrogen off of each one of the sides. Let's go ahead and throw this one up here because we know we can only have 2 around the hydrogen, but we need 8 around phosphorus. So 2, 4, 6, 8, octet rule is good. Duet rule is met. Our total that we can have is 8, and that's what we have, 2, 4, 6, 8. All right, so when we look at this, it's a tetrahedral arrangement. But what we're going to have are legs here, here, and here with a central atom. So the bond angles are 109.5 degrees, but I'm not going to have an atom up here at the top. So instead of a tetrahedral molecular structure, it's going to be instead a trigonal pyramid. And it's going to be easier to see once you see the ball and stick models in class as well. So it's a trigonal pyramid with 109.5 degree bond angles. Actually, it's going to be closer to 107 due to the fact that there's not another another atom out with that unpaired set of electrons. Let's look at selenium dioxide. Selenium is, has 6 in its outer shell. Oxygen also has 6 for a total of 12, so I have 18 electrons. So start with my Lewis dot structure. There are 2 oxygens and 1 selenium, so I'm going to put selenium in the middle of the 2 oxygens. Let's go ahead and fill the octet rule and see where we're at with the number of electrons. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. We have 18 total, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have too many. So let's first of all make that oxygen look better in the process. So let's do this. So we're going to, well, that's not much better. Okay, double bond here. So still we have the octet rule met, 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is what we're going to look at. So what's it going to look like? Well, we only have 2, so it's either going to be linear or it's going to be bent. And because there's a double bond on this end, we're going to see a bent angle on this one. So you have 120 degree bond angles on the SeO2. The O3 ends up being bent as well because it does the same thing. So let's look at oxygen is 6 times 3, which is a total of 18. So what we're going to do is we're going to put oxygen here, oxygen here, oxygen here, and let's see what happens with total numbers. Octet rule met for everybody. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Too many electrons. So we're going to get rid of a set, 2 sets here, and we're going to double bond here. So we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and we have another bent arrangement with a 120-degree bond angle. So that's as difficult as it gets with molecular structure. Knowing what the bond angles are, knowing what the molecular structure is, and the electronic structure are really important, but it just takes practice. And again, the ball and stick models you'll be able to use in class and be able to take home with you for your homework will help out tremendously with this. So in the video a while ago, this said 12.8. This actually takes you 12.8 through 12.10. So this is the last lecture for this chapter.